In this class, I'd like to start talking about a new problem, right? So we've done the particle in a one-dimensional box, and we've done the one-dimensional harmonic oscillator. Let's talk now about another problem that sounds like it might even be easier than those two. Okay, so let's talk about a free particle. That is a particle that's moving with no forces on it. Okay, so if there are no forces on it, that means the potential energy is just constant everywhere. So we could just say V equals 0. Let's choose the constant in the potential energy to be 0. So V equals 0 everywhere. So let's say from minus infinity up to infinity. That sounds pretty easy, doesn't it? Right? I mean, it sounds easier than the things that we have done so far. So maybe you're thinking, why didn't I do this one first? Well, and the answer is that the calculations are actually relatively easy, but there's something that's a little bit of a tricky concept that I'm going to show you coming up. Okay, so let's first go through the calculations, which we can actually do kind of quickly, and then get to the conceptual part that's a little more complicated. Okay, so we want to solve Schrodinger's equation the same as we normally do. Okay, so we have this time-dependent Schrodinger equation, the IH bar d psi dt is negative h bar squared over 2m times this second derivative with respect to x plus v times psi. Oh, but look how nice. This is just 0. Okay. So this is what we want to solve. Okay, so we do the usual separation of variables. Okay, so say the usual separation of variables. So as usual, we can assume that psi of x and time is some unknown function of x times a function of time. And we already solved the time-dependent part. We already know that the function of time is negative I energy t over h bar. Okay. So now this guy, this function of x, it must satisfy the time independent Schrodinger equation, right? Which is that the Hamiltonian acting on lowercase psi is equal to E times lowercase psi. So the Hamiltonian here is just the kinetic energy. There's no potential energy part. Okay, so that's minus h bar squared over 2m times the second derivative of lowercase psi with respect to x has to be equal to the energy times psi. Okay, so this tells us that the second derivative with respect to x is negative 2me over h bar squared times psi. Well, okay, so this is a differential equation that we've seen lots of times before, right? And so this is the differential equation where solutions are sines and cosines, or we could say the solutions are complex exponentials. So when we did something like this for the particle in a box, we chose the sines and cosines because that provided us with a good way to satisfy the boundary conditions. Okay? That we could pick just the sign solutions and just certain sign solutions. Now, let's choose the complex exponentials, and for reasons that I'll show you in a little while. Okay. So to pick the complex exponentials, again, we can say, let's take this quantity and call it k squared. Okay, so we have that k squared is 2m e over h bar squared, or equivalently, that the energy is h bar squared k squared over 2m. Okay, and then the solution for the time independent Schrodinger equation, we could write it with complex exponentials as one coefficient a times e to the ikx plus another coefficient b times e to the minus ikx. Okay, so this satisfies the time-independent Schrodinger equation. No problem. Okay. Now, we have separate solutions here with a positive number times x, positive k times x in the exponential, and a negative k times x in the exponential. We could say, let's allow k to be positive or negative. So in that case, if k can be positive or negative, then there's no need really to consider these two kinds of solutions separately from each other, right? They're essentially the same thing, okay? And so in that case, we just have that you could say the solution is just psi of x is a e to the ikx. Okay, so this is like the time, no, this is like the particle in a box, right? But now you'll notice that k can be any real number. K can be, say, any real number. And in that respect, this problem is different from the particle in a box, right? For the particle in a box, there were only certain allowed values of k, right? For a particle in a box, there are boundary conditions. And because of the boundary conditions, there are only certain allowed values of k. But now for the free particle, well, it's free and it can go all the way to infinity. So essentially there are no boundary conditions for it. And we can have any value of k, which means any energy E, h bar k squared, h bar squared k squared over 2m. Okay, so we've taken care of the particle, of the Schrodinger equation, we've taken care of the boundary conditions, there aren't any, right? And so in some sense, then we're done, right? So we could say, now let's go back to the time-dependent solution. That is this capital psi of x and t. So that's the lowercase psi of x times e to the minus I energy time over h bar. So this is a coefficient times a e to the ikx and e to the minus I. If I put in what the energy is now, and I cancel a factor of h bar, I get h bar k squared over 2m times time. Okay, so here's our answer, right? Or we could write it as a e to the ik x minus h bar k t over 2m, just like that. Okay, so there's the answer, right? And that was a lot quicker than the thing that we've done for the last two problems. All right, so now here comes the tricky thing. Okay, so we can say that looks good, but what's the problem? That looks good. Does that look good? That looks good. Exclamation point. What's the problem? The problem is for normalization. So suppose we try to normalize it. Okay. So we'll take the complex conjugate. So psi star of x and time. Okay, so that'll be this a complex conjugate times e to the negative ik x minus h bar kt over 2m, like that. Okay, and then the magnitude squared, so that's psi star times psi. Well, that's just a star times a, and the complex exponential factors cancel. So this is just the magnitude of a squared. So if we go to calculate the normalization integral, that's the integral from minus infinity to infinity of psi star times psi dx. That's the integral of just this magnitude of a squared dx. We're going to integrate that from x goes from minus infinity to infinity. Well, that's no good because that integral for sure goes to infinity, right? And so, you know, at the beginning of any of these homework problems I've given you, right, the part A of any question is, what's the constant A in the front that will normalize the function, okay? And here, there isn't any, right? That is no choice of A will make this integral equal to 1. Or in other words, the wave function is not normalizable. Okay, so this is a tricky thing, right? So we have a nice simple solution, but our whole procedure for interpreting solutions depends on the solution magnitude squared being a probability density, and here that's kind of breaking down. Okay, so what can we do, right, in this situation? Okay, well, there are two possible procedures here. There's a procedure which is described in the book, and there's an easier procedure that I like. And I like it because I have lower standards than the textbook author, right? And so the textbook authors, they are more sticklers than I am, okay? And so first, I'm going to show you my easy way, and then I'll show you the harder but more rigorous way that the textbook authors do it. Okay, so let's start with the easy way. I like things that are easy. My easy solution, okay, my easy solution is to say, let's work in a finite domain. That is, say, for x goes from minus L over 2 to L over 2. And then take the limit of L goes to infinity at the end of the calculation. Okay, so in my easy way, I would say for the normalization integral, let's say we want the integral from minus L over 2 to L over 2 of psi magnitude squared to be equal to 1. Okay, so that means then that this magnitude of a squared times the distance that we're integrating over, which is L, has to be equal to 1. Right? So if we solve for the magnitude of A, it has to be 1 over the square root of L. Okay, so we could choose to say psi of x and t is 1 over the square root of this artificial system size times e to the I kx times e to the minus I et over h bar, like that. If you do things this way, you can actually calculate stuff. Okay, let me show you some things that you can calculate. Okay, so we can calculate expectation values. All right, so if we want the expectation value of momentum, for example, let's see. So we want the expectation value of momentum. So that's going to be an integral of psi star times negative I h bar d by dx acting on psi integrated dx. Okay, so that means that we have the integral like this of a star e to the minus I kx e to the I energy t over h bar. Okay, that's the complex conjugate, psi star. Okay, now what? There's a negative I h bar. And now we need the derivative of the wave function. Okay? So this is a derivative of the complex wave function, the complex exponential right here. So the only thing that depends on x is in this complex exponential, right? So the derivative with respect to x is actually pretty easy, right? It's just ik times the function. Right? So, this brings down a factor of ik, and then it's all the stuff in the original function, right? E to the ikx, e to the minus I, energy t over h bar, just like that, integrated dx. Okay, now, once we've done that, right, we can cancel these complex exponentials in time. And we can cancel these complex exponentials in x, okay? And what's left, right? Well, excuse me here, I made a mistake in what I wrote, of course. This integral is not from minus infinity to infinity. It is from minus L over 2 to L over 2. That's the whole point of the thing I'm showing you, right? Is that we're doing the calculation in this finite domain. Okay, and then what do we have, right? Well, we have our factor of minus I h bar. We have our factor of ik. We have our factors of a star and a. And then this is all integrated for x goes from negative L over 2 to L over 2. So that just gives a factor of L. So this is all equal to h bar k. And let's see, this magnitude of a squared, that's 1 over L. And this cancels that L. So it's just h bar k. That's it, right? And now we can say, let's take the limit of L goes to infinity. No problem. It doesn't depend on L, right? It's constant with respect to L, okay? So in that sense, this calculation gives us the expectation value of the momentum is just h bar k. Huh, all right. What about the expectation value of the momentum squared? Well, that's going to be just the same, except we need two momentum operators in the middle. So there's a negative I h bar squared and a second derivative with respect to x of psi. Well, we can do this in just the same way, right? Because it's easy to take a second derivative of a complex exponential function. We just get two factors of ik. So there's this a star e to the minus I kx e to the I e t over h bar minus I h bar squared. And there are two factors of ik. So a e to the ikx e to the minus I e t over h bar dx. All right, now we can do this integral. And here we factor out the minus I h bar 2 powers of that, and the ik 2 powers of that, and the a magnitude squared. And let's see, all these exponential factors cancel each other. And we just get an integral, which is the system size L. So this gives us h bar k quantity squared. Right? And once again, we can take the limit of L goes to infinity, no problem. Okay, so we have values now for the expectation value of P and the expectation value of P squared. Okay. How about for the uncertainty then? So the uncertainty in momentum, that's the square root of the expectation value of P squared minus the expectation value of P quantity squared. So that's the square root of h bar k squared minus h bar k squared. That is 0. Okay. So this is the first example we have seen of a state with no uncertainty in the momentum. Okay, this state has a specific value of the momentum, which is h bar k. Now, if you are working with momentum and you get this, it makes you wonder what's going on with position, right? How can this be consistent with the uncertainty principle? Okay, so let's do the corresponding expectation values for position. Okay, okay, so the expectation value of x, this is going to be an integral minus L over 2 to L over 2 of psi star x psi dx. So this is just the, well, psi star psi is just a squared integral of x dx. And this integral comes out to be 0, right? Because we have an odd thing, x, which we are integrating over a region that's half negative and half positive. And what about the average of x squared? Okay, so the integral of psi star x squared psi dx. So that is a squared times this integral of x squared dx. So let's see, the a squared makes a factor of 1 over L. And then we have x cubed over 3 evaluated from minus L over 2 to L over 2. So it's 1 over L, and then there's a 1/3 L over 2 cubed minus the negative of that, so times 2. Okay, so this is what? It's L squared over 12. So that means that the uncertainty in x is equal to the square root of average of x squared minus average x squared. Okay, so it's the square root of L squared over 12, right? So that's L over root 12. Okay. And now we can take the limit as L goes to infinity, and this goes to infinity, right, as L goes to infinity. Okay, so that means that in this state, the uncertainty in momentum is 0. We know exactly what the momentum is, but the uncertainty in position goes to infinity, right? We have no idea where the particle is, right? We know that the particle has a specific momentum, but it could be anywhere from x's minus infinity to infinity. So that is consistent in this limiting sense with the uncertainty principle that the uncertainty in x times the uncertainty in momentum has to be greater than or equal to h bar over 2. Okay, so I kind of like that story because it's sort of easy, right? I mean, this wasn't a huge amount of calculations. Griffiths does not like that, right? Griffiths would say, what is this business of saying, you're doing a calculation in a finite domain and then later on you take the limit. Does that even make sense? Yeah, I mean, I respect he has a point that this calculation is kind of fuzzy in that way, okay? There's another thing that I just noticed when I was preparing for the class, which oddly I never noticed before in all the years I've been doing this. And the odd thing is that you'll notice that in this argument, the average momentum is not the time derivative of the average position, right? it's supposed to be, right? And we had a proof earlier in the semester, right, that the average momentum divided by mass is the time derivative of the average position, right? But that proof depends on the way functions being normalized properly. And this one isn't really normalized properly. And so, you know, that all breaks down. And so this is really not a very precise way to do things, okay? And so it's kind of a fuzzy hand waving way to do calculations, but it's not a real precise normalized way to do calculations. So the textbook author won't stand for it, okay? And so the textbook says, don't do that. The textbook says, what does the textbook say? The textbook says we need to consider states which are not just a single complex exponential like that, but instead are combinations of many such exponentials, okay? And so it says that we need to consider a state which is called a wave packet, which is the sum of many special solutions or separable solutions. Now that a single separable solution by itself doesn't make sense, but we can make a combination of many such solutions, and the combination will be okay. And the combination, so we'll call that a linear combination, right? The linear combination will be okay. The linear combination can be normalizable. So let me show you how to do that, okay? How to make a combination of these states which is normalizable, even though one of these states by itself is not normalizable. Okay. To do that, I need a mathematical concept called a Fourier transformation. So let me ask you about this. Has anybody taught you guys about Fourier transformations in your other physics classes or math classes? Okay, tell me, somebody, where have you learned about Fourier transformations?
Partial differential equations.
In partial differential equations. So you've learned about it as a method for solving partial differential equations. Okay, good. Was there something else, Ryan? Were you going to say something there?
Oh, just in math methods. So yeah, kind of the same thing.
In math methods, okay. How about in physics classes? Have any of you used Fourier transformations in any physics classes? Or Badur, I'll put you on the spot because you're coming from another university, right? So in your university, did they use Fourier transformations in any physics classes?
No, but just in math method.
In math methods, I see. So that's not my favorite way to teach things, right? Because I think it's good to use things in practice, okay? And so in a math class, you get one perspective, okay? So I want to give you a different physics perspective on what a Fourier transformation is, right? Because I have a feeling a lot of students coming into quantum mechanics have kind of learned a little bit about Fourier transformation, but maybe could use a refreshing. Okay, so I'm going to take a break from the free particle to do a sort of math refresher about Fourier transformations. And so I'll probably take, half an hour for this, like the rest of this class, and then I'll come back to the free particle tomorrow. Okay, so let's start with the idea of a Fourier series. All right, and because we talked about Fourier series earlier in this semester for the particle in a box. And so what I want to show you here is the way to sort of extend the concept of a Fourier series to a Fourier transformation, right? To show you how these concepts are related to each other. Okay. So let's say we're starting with the concept of a Fourier series, okay? And so, I told you earlier in the semester that a Fourier series is good for a periodic function with some periodicity lambda. Or it also works for any old function on a finite domain with a length of lambda over 2. So in either case, if we have a periodic function or a function on a finite domain, okay, we can write that function as a Fourier series with sines and cosines. Okay, so we could write it as f of x is a sum of terms from n equals 1 to infinity, an sine 2 pi n x over lambda, plus some other coefficients bn cosine 2 pi n x over lambda. Okay, and the sine and cosine functions, these things both have an average value of 0. Okay, so if your function f of x has an average value that's not 0, we better add that on separately. So we'll say b0 plus that. Okay, so this is one way of writing a Fourier series. Now, we could also write the Fourier series with complex exponentials instead, if we want to, because, as you know, the sine and cosine are combinations of complex exponentials, right? So we could say this cosine is 1/2 of e to the I 2 pi n x over lambda, plus e to the minus I 2 pi n x over lambda, like that. Okay, and likewise, this thing is 1 over 2i e to the I 2 pi n x over lambda minus e to the negative I 2 pi n x over lambda, like that. Okay, so in that case, we'll say, I don't like sines and cosines. I want to do everything with complex exponentials, right? So that'll work. And now I could simplify all of this stuff, right? I could say, let's multiply everything out, and then I'll have something times the positive complex exponential and something times the negative complex exponential. Okay, so in that way, I could get a Fourier series with complex exponentials. Right? So I could get a Fourier series with complex exponentials. That's basically the same thing as what I just did. Okay, and so that would be f of x is a sum over n equals 1 to infinity of something times e to the 2 pi I n x over lambda. Something goes there. Plus something times e to the minus 2 pi I n x over lambda. Okay? And the things that go in these places are going to be sums or differences of the A's and B's, okay, related to the A's and B's. But, I don't really care about the A's and B's anymore. So I will just call these things with new names. I'll call them C sub n and D sub n, like that. And there's still some coefficient up in the front, like that. Okay, we're good so far with the Fourier series with complex exponentials. Okay, now you might say we could make things a little simpler than this, right? Because isn't it weird that I have all the positive complex exponentials with the C coefficients, and then basically I have the negative complex exponentials with the D coefficients, and the 0 is a B thing by itself, right? I could just take the whole thing and make it simpler by writing the sum that's not over positive integers, but I'll make it a sum over all integers instead. Okay, so I'll write the sum as a sum over n equals negative infinity to infinity of something e to the 2 pi I n x over lambda. Okay, and then I'll say, oh, well, if n is positive, then this C is the same as that C. And if n is negative, this C is the same as that D. And if n is 0, this is the same as that B. Okay, so can you see so far how this is equivalent to that, right? It's taking everything and just writing it in a more unified way, okay? And so now instead of having, 3 kinds of coefficients there, there, and there, or 3 kinds of coefficients there, there, and there, I just have 1 kind of coefficient there, right? But it's the same sum. Okay, it's the same way of describing the problem. Okay, so this is now going to be my favorite way to write a Fourier series. Okay. And now suppose I want to know what are the coefficients. Okay, so I will get the coefficients by using the Fourier trick, where I multiply both sides of the equation by the function, the complex exponential function, and integrate. Okay. So if I want to calculate the coefficients. Okay, so I'll say, let's take the f of x, and I will multiply by a complex exponential e to the minus 2 pi I mx over lambda, where m is some other integer, right? It's any old integer. M is any integer. And that is a sum from n equals 1 to infinity, c sub n e to the 2 pi I n minus m x over lambda, like that. Okay, and then the Fourier trick is, let's now integrate over the full periodicity. Right? So let's integrate this thing for x from minus lambda over 2 to lambda over 2 dx. And the same on this side of the equation. Integral from minus lambda over 2 to lambda over 2 dx. And now I can simplify the integral on the right side of that equation. Okay, so now this on the right side of the equation is a sum over n of Cn times this integral of e to the 2 pi I n minus m x over lambda dx. And we can do this integral. Right? And what we get for this integral depends on whether n and m are the same integer or different integers. Right? If they are different integers, then we have an oscillating function in here. Sometimes it's positive, sometimes it's negative. Sometimes it's positive imaginary, sometimes it's negative imaginary, right? It oscillates over a full cycle or multiple full cycles, and it integrates to 0. That's if n is different from m. But if n is the same as m, then this is just the exponential of 0. Right? So it's 1 integrated over the cycle from minus lambda over 2 to lambda over 2. So then the integral is just lambda. Okay? So we put those things together and we say, we say this integral is lambda times the Kronecker delta, not L, excuse me, m n. Okay, and now we know how to do this sum, right? Because we have a sum over an infinite number of n values, but only one term in here is non-zero. It's the one where n is equal to m. That term gives us lambda times Cm. All the other terms in this infinite sum are 0. Okay, so that tells us then a procedure to calculate the Fourier coefficients. Okay, So far, what I can say about, how to do the Fourier series looks like this, right? We have a Fourier series defined as f of x is the sum of n equals minus infinity to infinity, Cn e to the 2 pi I nx over lambda. And the Cn coefficients are given by what we just worked out. 1 over lambda, an integral from minus lambda over 2 to lambda over 2, f of x e to the minus 2 pi I nx over lambda, like that. Okay, so this is what we've done so far. Okay. Everyone good with this so far? Any questions? Okay. So this is all, the regular Fourier series stuff expressed in terms of the complex exponentials. Okay, so now I want to make a change of notation. Okay, now that I've got you used to this notation, I'm going to change it. Okay, I'm going to say we don't really care about the integer n by itself. Instead, what we really care about is what multiplies x. Okay, so in both of these equations up here, we have an x multiplied by something. Okay, it's an exponential of e to the I something times x. Okay, and the something is 2 pi n over lambda. Okay, so we could say, n isn't really that important. What I really care about is this combination of things, 2 pi n over lambda. Okay, so I'll give that combination a name. Okay, so let's let K be that combination. And then I'm going to rewrite everything that I have so far in terms of K instead of n. Okay, so I'm going to get rid of the n's and put in k's instead. So let me do that. Okay, so that means then that f of x is a sum of c sub k times e to the I kx. Okay, and the allowed values of k in this sum are 2 pi over lambda times an integer. Okay. So, this is a sum over an infinite number of k values. And the thing here in this sum is nice and simple looking, but the allowed values of k are the things that I've written down there, right? 2 pi over lambda times an integer. Okay, and then I can put in what are the CKs that are allowed, right, from this kind of equation. Right? So CK, oops, CK is 1 over lambda integral from minus lambda over 2 to lambda over 2 f of x e to the minus ikx dx. Okay, so hopefully you can see that these equations are equivalent to these equations for the Fourier series that you know and love, or at least know. You know, it's just with this new notation. Okay. You all right with that? Okay, good, good. Now what? Now, I want to think about this sum, the sum right up here. So in this sum, we are summing over certain allowed values of k, right? I could like make a k number line. Okay, so here's a k axis, and I have a sum where k equals 0, k equals 2 pi over lambda, k equals 4 pi over lambda. Over here, k equals minus 2 pi over lambda, minus 4 pi over lambda, right, etc. Right? There's a number line for k, which has certain allowed values of k. Right? And I want to emphasize that on this k-axis, there's a certain spacing. Right? There is a spacing between the allowed values of k. Right? And that spacing is a delta k, which for sure is 2 pi over lambda. All right, so that tells us that lambda delta k over 2 pi is equal to 1. Okay. Now, with that, I want to rewrite these equations. I want to rewrite the first equation here in a slightly tricky way. Okay. So let's take this first equation. Copy. Let's try. Paste. All right, I copied a little too much. How do I fix that? I'll get my eraser. That's handy. Okay, good. So let's take this equation. I want to rewrite this in a tricky way by multiplying by 1. Okay, so I'm going to multiply by 1. Now, let me write a fancy form of the number 1. I will write this as lambda delta k over 2 pi, because I already showed you that that's equal to 1. Okay. Now, let's rearrange the factors slightly. Okay, this is a sum, k equals 2 pi over lambda times an integer. I'm going to put a factor of lambda over root 2 pi times ck there. Then e to the I kx, then delta k over root 2 pi. Okay, so you see this is correct. It's weird, but it's correct. Okay. Now, let's take this combination right here, lambda 2 over root 2 pi times ck, and I will give it a new name. I will label it as phi of k, like that. Okay, so f of x is this sum of k equals 2 pi over lambda times an integer of phi of k e to the I kx delta k over root 2 pi. And then I have my complementary equation that says, what are the coefficients? Okay, so now I want to know, what are the phi of k's? So phi of k, that is lambda over root 2 pi ck. So that is lambda over root 2 pi. And then my equation for ck is this 1 over lambda integral minus lambda over 2 to lambda over 2 f of x e to the minus ikx dx. And of course, these factors of lambda cancel. And the root 2 pi, I'll put it inside the integral under the dx. So I'll say an integral from minus lambda over 2 to lambda over 2 f of x e to the minus ikx dx over root 2 pi, like that. Okay, so here is my pair of equations for a Fourier series. Now, I've just manipulated it a little bit, right? But it's still the same thing, right? I've just changed my notation a few times. Okay. Now, here comes the trick, okay? The trick is, now I will take the limit of lambda goes to infinity. Okay. That means, you remember, I started with a periodic function of period lambda, or any old function on a domain of size lambda over 2, right? But in either case, if I take lambda goes to infinity, I get a non-periodic function on an infinite domain. Right. So I'm considering, any old function on the domain from x is minus infinity to infinity, right? As if it's a periodic function, but the repeating time has just gone to infinity, so that my whole infinite number line is one periodic domain, right? Or for my finite domain, I'm taking the size of that domain to infinity, right? So I can have any old function that goes up and down or whatever on the infinite domain. And so that means now, if I have my number line for k, I used to have a set of allowed values with a certain spacing. But now, if lambda goes to infinity, that means delta k goes to 0, right? Because delta k is 2 pi over lambda. So that means instead of having, specific phi of k's at the allowed values like this, something like that. Now my delta k is getting smaller and smaller. So I'm filling in all the spaces in here. Right? So that means instead of having a series of coefficients, the whole thing just gets smoothed out to make some function of k, like that. And what is the function? Okay, well, I have this sum right there, okay? And now, this is like the first thing you learned in integral calculus, right? When you were first learning integral calculus, you learned that you could take a sum of things like this, right? And in the limit of the spacing goes to 0, right? Very fine spacing, this thing turns into an integral, right? So the f of x, right? My old expression for f of x was a sum over allowed values of k, the 2 pi over lambda times an integer of phi of k e to the I k x, delta k over 2 pi. And this sum with a delta k turns into an integral dk. It goes to an integral of phi of k e to the I kx dk, and excuse me, this is a square root, over the square root of 2 pi. And this integral goes from minus infinity to infinity, right? Because k was already going over all positive or negative integers times the spacing, and now the spacing is smaller and smaller. So it could be anywhere on the number line, the k number line, from minus infinity to infinity. And to go backwards from f to phi to know what the coefficients are, well, that's the same as what we had before, right? Before we had this integral to get the coefficients, and we still have this integral, but now lambda is going to infinity. So that tells us then that phi of k is an integral of f of x e to the minus ikx dx over square root of 2 pi. Okay, so these are our equations for doing a Fourier transformation. Okay, so this corresponds to what hopefully you learned in math classes. Right? And the words that people say are that phi of k is the Fourier transform of f of x, and f of x is the inverse Fourier transform of phi of k. And hopefully from this, you see the connection between this and a Fourier series, and you can see the interpretation of the Fourier transform is to fill in these little gaps in the Fourier series, right? That the amplitude at any value of k, right? That any continuous value of k is allowed in this limit of lambda goes to infinity. And so now we can fill in all the gaps. And so we get this pair of functions, which are like partners of each other, f of x and phi of k. All right. That is my math lesson. I'm going to stop here because I've gone a few minutes overtime. Sorry about that. Let's come back to this tomorrow, and I'll apply it back to the free particle. Okay, see you guys then. Thanks.